Yeah, thank you very much for inviting me. It's a real pleasure to be here. My presentation is on whether we are on track with the Paris Agreement or not. And I could keep this presentation very short. If you basically look at the different pledges that countries have made as part of the Paris Agreement, it's very clear and visible that the emissions reductions that have been proposed by the different countries compared to the ambition and emissions reductions that are needed in order to stay within the long-term objective of Paris, which is to keep temperature well below 2 degrees or try to achieve 1.5 degrees, there is an enormous emission gap. So the ambition and the realities of the Paris Agreement do not fit together. Even if we look at the enhanced pledges by a number of different countries, including the European Union, that have been put on the table since September 2020, have reduced this gap basically only by about 10 to 15%. We have still a gap in the order of 20 to 25 gigatons, and this is roughly half of today's emissions. So we need by 2030 to reduce emissions much more dramatically or much more rapidly compared to the current policy signals. So what makes this target so ambitious is that the remaining carbon budgets, so the emissions that we can still vent into the atmosphere, are very, very small if you compare it, for example, to the historical emissions. Over the past, only 1/4 of the total emissions are left to be vented into the atmosphere. It's about 420 gigatons for a likely chance to keep temperature below 1.5 degrees, and this compares to 42 gigatons of CO2 emissions today, which means basically that at current rates in 10 years we will have exhausted that budget. Perhaps on the positive side, 2 degrees means something completely different than 1.5 degrees. For 2 degrees, the budget is roughly double, a little bit more than double as big as the 1.5 degree budget. And on the negative side, of course, 2 degrees means also something completely different on the impact side. So 2 degrees means, for example, roughly 1 billion people more exposed to extreme weather events with multi-sectoral impacts, as indicated by the 1.5 degree report of the IPCC. In order to keep temperatures to 1.5 degrees or 2 degrees, we need to achieve carbon neutrality. Carbon neutrality means that we have to achieve net zero CO2 emissions, and net zero CO2 emissions means that globally the aggregated system should not emit anymore. This does not mean that every activity on the planet needs to be net zero. It just means that different sectors that might emit into the future need to be compensated by other sectors that might act as sinks. And generally, if you look into the literature or into transformation pathways, sectors that remain positive are usually those on the demand side, which are more difficult to abate often, and then the supply side sector, so buildings, industrial processes, and transportation are more difficult to decarbonize than the electricity sector, for example. And hence those sectors in a zero emission system often are the residual emissions that are then compensated by negative emissions options in the supply sector, in the energy supply sector, as well as in the forest and land use sectors. Different models give you very different estimates about the need of how big these sinks need to be. This roughly between 5 to 10 gigatons, which means that in order to achieve net zero CO2, the emissions reduction need to be between 90 to 75% of current emissions, and the rest would then be compensated to negative emissions in those other sectors. Generally, the timing of the emissions reduction is very important. So if you speak about achieving net zero CO2 emissions globally by 2050, it means that some of the sectors actually need to achieve that even before this. So for achieving, for example, net zero emission in 2050, and it's shown here, you would need to achieve, in most of the models or most of the assessments show that the afforestation and land use sector is between 10 to 40 years earlier already net zero than the overall global system. Similarly, also the energy supply sector is 10 to 20 years earlier net zero, while the other sectors, particularly energy demand sectors, are net zero relatively later. In order to achieve climate neutrality, it is thus really fundamentally important to decarbonize demand and to limit particularly energy demand, which sizes the mitigation challenge since it determines the overall size of the system. And in my following slides, I want to focus a little bit on the demand side dimension, and particularly this study, which developed a low energy demand scenario that also has been selected by the IPCC. I would say there are two main perspectives in terms of how to achieve 1.5 degrees. The conventional perspective is that inertia in policy, social and technological change, and due to the upscaling of large-scale supply-side options and infrastructure, lead to overshoot in the medium term that needs then to be compensated in the long term to negative emissions technology. So you have an overshoot because of the inertia of the system, and then you have in the long term negative emissions technologies that can basically lead to a negative emission system. The other perspective focuses on limiting energy demand and achieves rapid transformation driven by a fundamental change of the demand side sectors and to end-use innovation, but also to behavioral change. Such a system relies on granular, distributed and supply-side options, which can diffuse more quickly into the system, and in the long term also avoid the reliance on the negative emissions technologies. Limiting energy demand to very low levels requires also new trends, particularly new trends in social and technological change. It means changing consumer preferences, for example, switching towards new diets. It requires, to some extent, value changes, enabling new lifestyles and behaviors. It means also new business models, moving away from ownership models to a more shared and circular economy. And finally, it means also to find ways to benefit from digitalization, ICT convergence, to accelerate innovation and build that innovation on granular technologies with integrated digital devices. Some of that we see already. So if you look into our cities, we see increasing shares of electromobility, we see increasing sharing of vehicles, deployment of electric bicycles are quite successful nowadays. But all of those changes are very embryonic. And what we really need is pervasive, disruptive end-use innovations on multiple scales and also in multiple sectors. Generally, these different I cannot go into the details of all of them, but generally what all of them have in common is that we first switch from a system which is based on ownership to one which is based on usership. So not owning a certain service is in the center, but the quality of that service and its use. And the convenience of the service at the end. And this requires, of course, certain value changes. So you don't owe the car, but at the end you are interested in the best quality service to get from A to B when you need to get from A to B. The second is sharing those devices in the economy. And the third is to move from atomized, disconnected technologies to connected technologies. The connections between them provides the utility to really change the way that our system is organized at the moment. And basically it means also at the end to move from our current system where everybody owes a certain device or appliance to a system where appliances are shared and where you have an internet of things that people share with each other, but with higher quality perhaps that they could afford if they need to basically get the device themselves. Rapidly changing the system is also, as I mentioned earlier, much easier if one relies on granular technology with smaller unit sizes, lower unit costs, which are modular, and also a lower risk in terms of the investment. This is particularly shown if you look into the learning rate of different technologies, in this case energy technologies of the past. Generally, if you look at this figure here, you have the unit size of different technologies. Here you have the learning rates of different technologies. As you can see, when the unit size increases, technologies learn slower. Some technologies have even negative learning rates because of this learning. And the rule of thumb is that you have smaller unit sizes, you have more units if you deploy the same, let's say for the same output, and you have more opportunities to experimentations, thus the learning and the cost reductions are more rapid for this type of technologies. Another big advantage of granular technologies are the equal distribution that can be achieved in a much more easier way. So the low energy demand scenario by group like AL that I've previously mentioned achieves per capita energy services in the south much more rapidly than in the conventional scenarios. And if you think about food, thermal comfort, consumer goods, and mobility, the minimum level of mobility, so that people, for example, reach hospitals or schools and so on, those can be much more easily distributed among the poor, and you can reduce energy demand overall quite a lot by at the same time making sure that everybody in the world basically appreciates a certain minimum standard, minimum decent living standard. This is much easier with small-scale technology. And then finally, I think really critical for this transformation, if it's driven by the demand side, is to benefit from the digital convergence. So technologies like the mobile phone are a good example how different services can be combined and converged into one device. And the mobile phone replaces, in terms of its utility, a number of different other devices, from the camera to the TV to remote controls, etc. And at the same time, by providing perhaps the same service and often better service, it significantly reduces, of course, the energy use. It significantly reduces also the embodied energy as well as the material use and the standby energy use of those the alternative devices together. So in my final slide, I want to focus on the economic dimension and particularly emphasize a recent insight from the latest literature, which very nicely shows across very different methodologies applied the main difference in terms of the economics of the blue and the red line here on the left-hand side. Basically, delaying near-term emissions reductions means overshoot of temperature targets, particularly 1.5 degree, but also the 2-degree target, compared to investing now, which means very rapid decarbonization. And in the long term, actually means that we don't need to rely on net negative emissions. Doesn't mean that we don't have CDR, remember, but it means that we don't have it on very large scale. And economically, this actually means that we have upfront investments in the near term, so costs in the near term, which are by far more than compensated because of tipping points that we can achieve in the long term. So across all different integrated assessment models which run this experiment on the left-hand side, all of them actually indicated that if you're going to the upfront investment and the near-term costs, in the long term the economy will gain. Even if you don't take into account impacts, the economy will gain in the long term. So that's I think that's a very important conclusion of the recent literature, and a positive ending perhaps to my presentation today. Thank you very much for listening.